All right, let's jump right in. Have you ever stopped to think about how all the complex machines on a massive ship actually talk to each other? I mean, you've got the engine room, the bridge, dozens of systems that have to be perfectly in sync. So, how do they do it? What's the secret language they're all speaking?
Think about something as simple as a fuel tank. How does a physical thing, the actual level of fuel, get turned into a number on a screen that an engineer can trust with their life? Well, that's exactly the mystery we're going to unravel in this explainer.
Because for a ship to run safely, all these different electronic brains, the big PLCs, the little microcontrollers, all the monitoring panels, and of course the alarm systems, they all have to speak a common, super reliable language. They need to know what's really happening out there in the physical world.
And that brings us to the hero of our story today. It's an elegant, it's simple, and it's an incredibly common solution, the 0 to 5 volt DC signal. This little signal right here is one of the most fundamental ways machines translate our world into data they can actually understand. So what is it exactly? Well, a 0 to 5 volt signal is what we call an analog signal. That just means it can be any value between 0 and 5. The easiest way to think about it, it's like a dimmer switch for a light. Turn it all the way off, that's 0 volts. Crank it all the way up, that's 5 volts. And every single level of brightness in between, that corresponds to a very specific voltage. The voltage is the message. And this slide just lays it out perfectly. Check it out. If a fuel tank is totally empty, the sensor sends out 0 volts. If the tank is completely full, boom, we get 5 volts. So what about a tank that's exactly half full? You guessed it. The sensor outputs a precise 2.5 volts. It's a straight line, a totally predictable relationship. So simple and so effective. Okay, so why this signal? I mean, what are its superpowers? Let's dive into why engineers just love using 0 to 5 volts, especially for all the communication that happens inside the control panels and the electronic brains of the machinery. Well, there are 4 really big advantages. First off, it's super simple to process because a ton of microcontrollers, like the Arduino you might have played with, they're already designed to think in 5-volt logic. Second, it's incredibly easy for something called an analog to digital converter to take that smooth signal and turn it into a hard number that a computer can log and analyze. Third, it's really low power. It just sips electricity. And finally, it's absolutely perfect for short distances. And believe me, you find this signal everywhere. It's inside engine monitors reporting temperature and throttle. It's in the tank level sensors, the ECUs of modern engines, even inside navigation gear. It's a real workhorse for that internal, close quarters communication, assuming, of course, the conditions are right. But you knew there was a but coming, right? Here's the twist. As great as our 0 to 5 volt hero is, it does have a weakness. And the harsh, noisy environment of a ship's engine room, well, that's a serious challenge. Yeah, an engine room isn't some quiet, sterile lab. It's a chaotic world buzzing with powerful motors, huge generators, and massive high-current cables. And all of that chaos creates the #1 villain of our story, electrical noise. It is the absolute kryptonite for a clean, precise voltage signal. See, this noise can literally jump onto our 0 to 5 volt signal, distorting the message and making it totally unreliable. On top of that, if you try to send this signal down a really long cable, the voltage can actually drop along the way. That 2.5 volts that meant half full might show up as 2.4 volts at the other end. Your reading is now wrong. The message gets weaker the farther it travels. And this is where a different kind of hero has to step in. For those longer, tougher, noisier battles, engineers turn to the industrial heavyweight champion, the 4 to 20 milliamp signal. Now, instead of measuring voltage, think of it as electrical pressure. This signal measures the electrical flow, or the current, and that, my friends, makes all the difference. Let's put them head to head. This table really shows the trade-offs. The 0 to 5 volt signal, not so great with noise or distance, but look at the 4 to 20 milliamp signal. Its noise resistance is high, and it's a long-distance runner. Sure, it uses a bit more power, but that's why its industrial reliability is rated very high. It's just built for the tough jobs. So what this all really boils down to is a classic engineering principle. You got to use the right tool for the right job. It's not about one signal being better than the other one. It's about understanding the situation and choosing the one that fits the application perfectly. And this expert insight just nails it. You use 0 to 5 volts for the short, clean communication inside a control box where everything is tucked away and close together. But for connecting to a big industrial sensor way out in the noisy engine room, you go with the robust 4 to 20 milliamp signal every time. So, The crucial takeaway is this: 0 to 5 volts is your hero for local internal tasks. 4 to 20 milliamps is your hero for the tough, long-distance industrial work. And for any technician or engineer out there, knowing which language is being spoken is absolutely critical for troubleshooting and keeping these incredibly complex systems up and running. It's such a simple concept, but it has these huge implications. And it kind of makes you wonder, doesn't it? From the thermostat on your wall to the car you drive, what invisible signals, what secret languages are running all the systems all around you right now?